you should
yeah, more or less, let's say. Just a long people out. Okay, so today is sigma algebra of Lebesgue and various properties. So last time, basically, we arrived to the following thing. The measure me, so we have the three objects. So we have the definition of sigma algebra. So it is an algebra, so it's closed under, well, union and intersection and complementation. It contains the empty set. And the sigma means that it's closed under countably many operations. Countable union, and then by complementation, countable intersection. Then we have the definition of a measure. On a sigma algebra. Okay, so it is a function gives zero, gives the empty set the value 0. It takes only positive measure, positive values, and okay, it's nice because well, you want to be sigma additive. This is the other important property. So the measure of a countable union of this joint set is the sum of the measure of all sets, of every set. So, and the sigma algebra being closed is okay. The domain is correct. And finally, we have the other object, which is, well, if we relapse the additivity, the sigma additivity into the sigma subadditivity, so we can have functions which are defined on the power set of R, or the power set of any set. And the thing is that we know, or we will see later, that this cannot be done preserving. So in general, at least for the Lebesgue measure, but even for more general measures, in general, the sigma algebra cannot be the power set. Okay? So remember, I have to relax something, so this is the alter, the Lebesgue, outer measure, M star. And so the fact is that M star is defined. So you have a way to compute M star. No? The important thing about measure theory is that the rules are very easy in some sense, but the construction are difficult, and it's very close to chess. The rules are not complicated, but the tactics can be very complicated. So the important fact about all this stuff is what is M star. So the only thing I can compute now. The rest is just theoretical stuff, no? I put some definition and say if they exist, it should be like that. But the first thing I really can compute is M star. You remember the definition? This is really the most important thing because it tells you how to compute things. So M star of every set E of A, let's say A is in the power set of R is equal to what? Is the infimum. So let me write like this. Infimum of the sum of the length of intervals where A contained in the union of the intervals and these are open intervals. Okay. And now the thing is a little bit strange. So, well, a posteriori is that while, well, you see that, we will see that it works. But then a priori, why is the definition is, so definition, E is measurable if, so it's defined to be measurable if for all A contained in R, the outer measure of A is equal to the outer measure of A intersection P plus the outer measure of A minus P. I really thought if you arrive at this point, why you need to have this definition? It becomes natural. I have to say that I didn't find any reason. Well, okay, some reason, yes, of course, because I say that in order to be measurable, you should have some sort of additivity instead of subadditivity. And so let me put a remark. So this is a definition. You give me a set, I have to prove that this holds for any other set. And this I can compute, I can compute, I can compute. So which part is difficult or, so okay, equality means that one is less than the other and then the opposite. So which part is the easy? Yeah, recall that this one is subadditive, no? We said it's one. So one part is easy. So the two, it's only to prove that M star of A, M star A intersection P, M star A minus. The other is automatic. Maybe you can find any reason. I have to say that I can see why naturally one has to start this. I mean, you have to do some trials and errors before arriving to the formula, but we don't have time. Okay. So now the goal today is to prove that this definition of measurability generates a sigma algebra. And the measure, the outer measure restricted to this sigma algebra is our Lebesgue measure, the thing we were looking for. So the goal the immeasurable is a sigma algebra, and M star restricted to it is a measure. And actually this is M, the Lebesgue measure. Okay, so finally we constructed. At the end of this lesson we have the Lebesgue measure. Okay, still you can say it's not really constructive here. Well, yes, I have to check what is E, and well, give me E, I have to check with all A. This is something you don't like. Well, at least if you want to have a constructive way, because it's impossible for me to check for all E. No? You understand? However, at the end we will see of the lesson that there are some regularity theorems, which basically allows you to say that the measurable sets are essentially countable intersectional open sets or countable union or closed sets plus sets of measure zero. And this is okay in some sense, because essentially it tells you, okay, essentially have open set and countable intersection of them. And then I play with it. I can add some very little piece. Understand, no? This is it's a little bit difficult comment, but it's important because this is constructed, these are definitions, these are just definitions. So I deduce things from definitions. This is the way I compute. This is a definition, I deduce this thing from definitions, but then I give you a way to check easily. Okay? Okay, let's start with some easy observation. Lemma Okay, E measurable. So, okay, let's do a definition. So, let's say the set of measurable set, let's call this M. So, I will shorten it. At the end, this will be the reflexive margin. So, which means E to this class, let's be correct, to this family of sets. Then R minus E is measured. Questions here? Proof by definition. And I will not add anything. So it follows immediately from the definition. Okay. So let's see the line. Okay. Proposition. The outer measure of E is equal to 0, then E is measured. I will just say the ingredients. Monotonicity, which I recall means that if A is contained in a prime, M of A less or equal than M star of A prime plus the definition. Plus the remark. Okay, let's say the remark. So now the line is questions here. You know how to complete the steps? You don't know? Otherwise, I ask the people that have some trouble to try to complete them. You know how to complete them? No. Okay, so let's try. Okay, monophonicity plus definition. So what do they imply? So let's apply monotonicity with the assumptions to the definition.
Measure of the intersection of the other one is equal to 0.
How much is this one?
0.
0. So now let's use again the monotonicity.
The measure of A minus E is less or equal to the ratio.
Yeah. We add the two. Okay, so we obtain that. Now, the remark. Now the remark. So if I add 2, I obtain this inequality, and by the remark, it's equality. Or E is measured. Okay. Now let's have some fun, because this is quite simple here. So let's cancel it. We take just we keep only the definition. if ei I from 1 to n are measurable, usually you should say Lebesgue measurable, because I'm using the outer Lebesgue measure. Here we have just considered the Lebesgue measure so far, and then we will do something more complicated. Then the union of EI is Lebesgue measure. Okay, I just make a drawing now. And then I ask you to complete the proof. The drawing is well, as usual, when you do drawing, when in set theory, you just have to consider, just to organize all the possibilities. No? So now I put E1 and put E2. So now I have the all possibilities, the triple intersection. Okay. Now we have just to use the definition up there and do for E1 and then for E2 and then rearrange things. Does anybody wants to try? Or, okay, I will start and then you'll say the next. So M star of A. Okay. Okay, let's use E1. E1 is measured. So I use the definition. Equal to
M star of
okay, let's cover the two parts. So the M star of A is the M star of this plus M star of this. Next step.
We remove E1 from E2.
Okay, what we want to prove? Because yes, we can do several, but we have to, what do we want to prove? We want to prove that, so at the end we want to prove the union, no? So it's this set plus this set, okay? The union should be measurable, so it's M star of the intersection plus M star of the subtraction. So far I have the green and the yellow. So one of the two sets on the right hand side should be split into two more parts. And then I want to add this part to this guy. Understand? Okay, so what do I do?
We can split A intersection E1 is also a subset of R, so we can use the fact that E2 is measurable.
Yeah, but then you obtain this little triangle. But I want to have the other piece. I have already the yellow piece. I want to add this small triangle. This is the other one.
Yes, yes.
You see, no? Okay, that's it. So this one I keep, because this one is already okay. So it's M star E1. And now I use that E2 is measurable. So it's M star of E minus E1 minus E2 plus M star on the border E minus E1 intersection E2. And now I have the pieces, no? So I have this yellow one which is this one. I have this orange one, which is E minus U1 intersection E2. And finally have E minus U1 minus E2, which is this nice green one. Okay, now what I do? I want to have that. So at the end, I want to write, and this is what I want to put, is M star of E intersection E1 union E2 plus M star minus E1 union E2. So how to do the last part? Okay, this guy is already here, no?
Yes.
So it's okay. And then is it true that this sum is equal to this? So it's the yellow plus the orange. Okay. So take this set. E1 is measurable. So this set intersection E1 is clearly A intersection E1. And this set minus E1 is A intersection E2 minus E1. Okay? However, the proof is not finished. Why?
Because we have n.
Okay, how to do for n?
Induction.
Hmm?
Induction.
Yeah, induction. Yes, you repeat. Well, this is fine with me, just repeat. So for n, just repeat. So you'll use this one as so once you have the measurability of the union, then you know that E plus E1 is E1 plus E2 is measurable, and then you can add E3. Okay. Well, we are close, no? To the sigma algebra. So now at the end, now the proof tells you why the definition becomes a little bit more natural. Sorry. I the end is joined. From I equal to 1 to n. Then M star of A intersection the union of Pi is equal to the sum M star of A intersection Pi. So now we understand why this is the case. At the end, when we write that one with counter-Limeni, you say, yeah, this is, well, I should start with the counter-Limeni, because I want to have countable, the countable additivity. But then I discover, well, after doing some computation, that just require two additivity. Just additivity is fine. This is my only explanation where I write that. But okay. Okay? proof basically is the same there. So maybe I switch, because there is one part which does not appear. So you see, this part is not there, no? So we repeat the proof. What happened is that so now I have okay, a measure of A intersection the union is the measure of A intersection E1 plus A minus E1, which is E2. Maybe we, but you want me to do that or not? Depends if you feel it or I can do that. Okay, so I follow you. I just start with the line. The line is exactly the same. I only observe there is one part missing, and so I get that the equality. E1 measurable. But now, okay, this one is exactly M star. And now A1 and M2 are disjoint, so this guy is just and then for N I just repeat, no? You see, in that case what I have that this part here being missing, one of the terms is not, does not play anymore, or is equal to one of the terms I just brought. Okay, so conclusion so far is that M is an algebra. We said that it's symmetric, the definition, by taking the opposite, the complementary set. Then it's countably, finitely additive. Well, finitely additive, sorry, that's it for the measure. It's the countable, the finite union of sets belong to this family. So the M is an algebra. And the measure M star, well, it's basically additive on the algebra. So let's do that. The final thing is that the union of, so let me keep this guy. Then the union is measured. I know it's a little bit boring here. Maybe we'll do some exercise later. Let me finish these two parts. And then we arrive to the some exercise. Okay. Well, the thing is always the same. M star of A is equal to. Okay, I take finitely many. So for all n is M star of A intersection the union up to n. Plus M star of A minus the union of E I. But now here I have that this thing is, I thought I switched the proof. So here we already proved that this holds. So this is the sum of m star of A intersection EI. And okay, and then okay, keep the rest.
They are not disjoint. Not necessarily disjoint.
Yeah, right. That's what, there was something that, and disjoint. There was something that I didn't feel like, I forgot to say this disjoint, yes. Indeed, there was, that's why. Because at some point I thought that I was looking to another proof, but then the proof that for the general sets, it was, well, the proof is just an application. Once you have this joint, you take the union is the countable union of this joint set. That's the same. Okay. So now I say that if I subtract the union from I to infinity, okay, this set is smaller, no? So what I get is certainly larger than the sum m star of A EI plus m star of A minus the union up to infinity of EI, because this set is small. I subtract a little bit more. So now this holds for any n, and the sum from I to infinity is exactly the limit of this partial sum. So taking the limit, I obtain exactly what I want. M star of A is greater or equal than the sum of M star A intersection EI plus M star A minus the union of EI. Okay, then apply the remark, and this says that this is measurable. And you see that at this point you understand why that definition was okay, because this is if I say something is measurable if this sum hold, you would say
Here we have finite, then the sum is outside. Yes, the sum is outside for infinite. And how to bring it back inside the measure?
which one the sum.
The last line.
Yeah.
Yes, we have infinite sum outside the measure.
Yeah.
And why is it true if we put the union, infinite union, inside the measure?
How to put the note inside what we want to have the union inside?
Yes, and why is this equal to the?
Oh, because we are proving the measurability. The measurability means that m star of A. Okay.
I mean.
Yeah, you're right. Sorry, you're right. This morning is not my perfect day because of countable subadditivity. You're right. I'm confused because of the next point for some reason. I don't. So now I use countable subadditivity. Which says that the measure of a countable union of sets, so and this is a countable union of sets, is less or equal, so okay, this is m star of this is less or equal than the sum of m star. Yeah. And so you get. Thank you. And so now you get finally M star of A, the sum, so I replace it with this guy, M star of A intersection the union, plus M star of A minus the union. Yeah, you were right. I was thinking about the next proposition. For some reason, I switched I have this proof coming up in my mind. So the next statement. Okay, so corollary. I is in M for countably many sets. Then the union of EI is in M, even if they are not disjoint. Proof I leave for exercise, because it's just set theory, basic set theory. So conclusion, let me see, because I wrote, okay, conclusion. M is a sigma algebra. Complementation was okay since the beginning, and after this long route, I arrived to say that the countable union of sets is is closed under countable union. And okay, all this long route comes because I take a definition which is very basic, just the sum of two sets is equal to the measure of the set. But I could have started with a more complicated definition. In the end, the thing happened to be the same. So just to let you know why the things are strange. Okay, so far so good, but then still something missing, is that everything here is completely theoretical. Do you agree, no? I write a sigma algebra done by this definition, and I don't know which kind of family of sets is. So can you say that, well, the empty set certainly belongs, the complement of the empty set belongs, but then other sets you don't know. Sets of measure 0, so the rational number, then the irrational numbers, but then it becomes a little bit more tricky. Because what we want to measure are at least intervals. Okay, so let's do the next step. Intervals are measured, the back measure. Okay. How to do that? It's up to you. I do some suggestions. Let me say, but I think the way that the book does, well, it's correct. But it's better to have some fun here. So let's see as an exercise to be solved in class. But what I have to prove is written up there, no? And even the inequality is enough. But may I suggest just the following? Let's do as the book does, simply because you have only to consider one case instead of two cases. So it is enough, so the remark, it is enough for A plus infinity. Why?
Because we prove that it is stable by complement and union.
Intersection, union, whatever, so you get closed, and then you can remove a point, or can add a point. Why? Is a point measurable? Yeah, so we measure 0. So I can close it, open, whatever. Just if I have an interval A, B, I have to consider two sides because the problem will be in A, no? Clearly R is measurable. So whenever a set A is contained into this interval, this open half line, you don't have, the equality is clearly true, simply because this is 0. So the problem is when A crosses, well, capital A crosses small a. Okay, so let's do for capital A crosses small a, let's do a drawing. It's just, in my opinion, helps. Okay, so this is A. I'm taking the open set here. And let's say I have a large capital A over here. So I draw like this because it's a complicated set, no? It's A also here. Okay, now definition. I don't have many tools. As I told you, I just can play with definitions, and actually is the best way to do, in my opinion, measure theory is always to start with the definition. Otherwise, you write things which are completely crazy, and it's very easy to write things that are crazy here because we are really at the bottom of the theory. Okay, so definition. So let's measure. So to prove the opposite inequality, I have to construct a covering here and a covering here. Okay, such that essentially, when you give me a covering here, and then I construct a covering of these two which have the same value. You understand, no? So I give, this one means that essentially you give me a covering which is very close to the value. And now I use that covering, maybe I just replace one point, which by the way will be A. And I construct two coverings, one of this set, one of the other set, such that the total length of the covering is the same. And then I say that, okay, M star is less or equal than the covering, and I get the inequality. So, okay. So the first step is that I give you a covering of this capital A. And essentially the covering of this guy is such that M star, I'm trying to make it graphic, because I hope you remember that. A is like the sum of the length of these intervals. There is one remark here. I'm assuming that M star of A is finite. Otherwise, that thing is a little bit more difficult to use. I cannot subtract. But if it is infinite, clearly there is nothing to prove. This is plus infinity, and this is clearly less or equal than plus infinity. Okay. Now construct the two coverings. So
intersection E.
What I do? So with specific covering, which interval should be broken?
Yeah.
This one, no? So this interval here, we break how? Okay, I take this interval here. They should be open intervals. I can take this open interval here, and then what about the value A, small a? What I do about the value?
It doesn't change anything.
Exactly, let's measure 0, I don't care. So let me define a covering of this guy. So if I is a covering A, then I intersection A plus infinity is a covering of A intersection A plus infinity. I intersection minus infinity A is a covering of A intersection minus infinity A. And so I get that. And A is measurable. And M star of A equal to 0 implies M star of A, capital A is equal to 1 star A minus A. Okay, these are the 3 points, and then I have just to combine them. And then I know everybody understands how to combine them, but I ask you to do that in the correct way. So we have to reach checkmate in 3 steps. Okay, who wants to start? It's already late. M star of A. Third step. And now I would say that this guy is larger or equal than the sum of, okay, I take these 2 sets. So let's call this set I plus A, and this set is I minus A. I minus I, sorry. So on the left hand side. So is the length. Because I choose the covering I such that this measure is essentially done by the sum of the length. And what happened is that, so again happened for this guy, and then, well, this is just the definition. There is an epsilon since it's finite measure such that this holds. Now this guy here is an open covering of the other. On the plus side. This is an open covering on the left side, and so by the definition of M star, it's the infimum. And then it's done, no? This for every epsilon holds. It's okay? It's very boring, I'm sorry, but this part is a little bit boring. At least we have to prove it once. Conclusion. This is an important definition. If the Borel set of R is the smallest sigma algebra containing the intervals, the open set, then what I deduce from this proposition
It's a subset of the
is measured. Then B of R is a subset of the measurable set, the Lebesgue measurable set. Okay, and then I say the following. The Borel set is an object which you can construct. I mean, there is a procedure, a countable procedure, of course, cannot be finite, but we allow countable. Countable means that you can be as close as you want with finite many operation, which allows you to construct the progressive value. There is an explicit representation in terms of countable intersection of open, countable union of countable intersection, countable union, countable intersection, countable union, countable intersection. You do that thing at most countably many times. So it's a countable operation. And then we have this relation. So it's almost, we know what is M, because this depends on your interpretation, but B of R can be computed with the precision you want, in some sense. So we know what is M. And the last thing is that, well, I will not say it. Let's do some exercise now, just to see. Right. Now I can cancel this definition, we don't need it anymore because we already have the algebra. M and B are translation invariant. So if I take a set in M, these translations are still in M. But that's it's okay, no? M star is the translation invariant, and so this proves for M. And B, well, is generated by open sets, so that's translation. Now, prove that if what is the measure of E is let me see what I want to say in this exercise. Okay. Is greater than 0, then there exists n natural number such that the M of that is E is measurable. From now on, essentially E is measured. M of E intersection minus n is greater than 0.
E is measurable.
Yeah. From now on, we take measurable sets. Non-measurable sets, they are gone. But at least when we arrive to the point to prove that they exist, at least to give the hint why you, with the axiom of choice, you have a non-measurable set. We will see that hint how to prove that. I will not give the proof because, in my opinion, it's a little bit. The axiom of choice is something, is a bad piece. But okay, at least to know that the situation can be complicated. So from here, how to do that? So I add another exercise. So if M of E is less than infinity, then for all epsilon, E is the union of sets Ek such that I finite, such that the measure of EI is less than epsilon. For every epsilon, you can partition the set into finitely many pieces of length epsilon, of measure epsilon. Okay, you know how to do that? This part is easy. M. From now on, we use well, you can have some similar statement from for n star. But from now on, we use the measurable sets. The non-measurable sets, they do not exist, basically. Question here? Okay, let this one, it's easy, but let's say this one. Why should be the case?
The countable additivity.
Countable additivity. Because otherwise it turns out that if it is 0 for any n, so it's 0 for any countable in many pieces, minus n, minus n to n, and then you add it in the real line. So the measure of E is 0. Okay. So now we talk about the regularity. Theorem. Equivalent properties. This is a very important theorem. It's really important. You will see in different ways. So this is essentially this is the elementary version for sets, but for function there is something completely equivalent. So E is measurable. For all epsilon, there exists open set. E is contained in the open set, and the measure of E minus, the open set minus E is less than epsilon. Or, here I have to use M star because I don't know if it is measurable. C. For all epsilon, there exists a closed set such that C is contained in E, and the measure of E minus C is less than epsilon. D. There exists a G delta set E is contained in G. G delta means that it's a countable intersection of open sets, no? Countable intersection of open sets, and the outer measure of G minus E is equal to 0. There exists an F sigma. F sigma is the countable union of closed sets, is the complement. Countable union of closed sets. F is contained in E, and E minus F is equal to 0. Okay, before proving the theorem, after this theorem, essentially, we know which are the measurable sets. And this is very important to remember, because it happens often that you have this measurable set, but then what is a measurable set? I can really build it? Yes, essentially with this theorem, yes.
Form measures to a Borel set.
It's
Every measurable set is
a Borel.
a union of a Borel set and measures zero set.
a measure zero set. So the only space where you can play with the construction of a measurable set is in zero, in set of measure zero. You see from this fact, it say that E is between a F sigma set and a G delta set. So you have this very little, very narrow thing that is where you can put arbitrarily choose which one belongs to E or not. For the rest, you don't have any other choice. And so the axiom, you see now that how many measurable sets depends on how the freedom you have to choose this. And you observe now that, well, how much that the set theory, well, the axiom I can use, they play a role. But they are not, this is really powerful thing. And before proving it, which statements are equivalent by trivial set operations?
So maybe to
Hmm?
BC.
BC, adjust inverted. And then DC, DE, they adjust by complement. So because counter union, the complement of counter union is a counter intersection of closed, the open closed. So let's prove now A, B, D. They are equivalent. Okay? Okay, we stop here and then we do some exercise just because yeah, the two theorems, still two theorems. Okay. Okay, E is measurable. What I use now? So I have E, I have this O, which is built by, well, it's something which has essentially the outer measure of E. It's a open covering, and then what I use? Okay, I can take M of O is, let's say, okay, let's assume always E finite. I don't want to treat the infinite, you can do that. So it's less than M of E plus epsilon. This is by definition of the Lebesgue measure, no? Because it's concerned with the outer measure. Then I have to use measurability. By measurability, so here it means that E measurable. And now, if I compare the two, I obtain that this guy is less than epsilon. So both of them implies B implies D. This is very easy. So the assumption is that for all epsilon, there exists open set, open contains E, let's say, or let's make it depends on epsilon and star of E, sorry, O minus E is less than epsilon. Or what are you, the trivial thing? What are you?
Epsilon equals 1/n.
A sequence of epsilon goes to 0. Which sequence you like more?
1/n.
Okay. And what will be now the G delta G? Then, with a star, be careful, I can use only subadditivity and monotonicity. I cannot use the super. So I have to be careful which part. Well, but now this is the easy part. G is contained in On. Okay, so it is 0. Okay, and now this, we did already in the exercise. Because this says that M star of G, sorry, this says that M star of G minus E is equal to 0. And I know that for a set of measure 0 is measurable. Okay? So it means that E is a G intersection, the complement, no? R minus, okay, let me write just the complement. G minus E, is G intersection no, wait a minute. So the measure is 0, so I want to say that G, I subtract this piece here, and so this, so E is the complement of G union G minus E. Complement. The complement of G union G minus E. Okay, now it's clear. So this is measurable, this is measurable, the union is measurable, the complement is measurable.
Well, I have a question.
Yeah.
How to do if the measure of A is not finite?
Exercise. Is that exercise? The trick is that you can just restrict to intervals and then you can add. Because you know before that essentially if it is measurable inside each interval, is measurable everywhere. And now all the statements restricted are the same. So here you need just a sequence which converges. Yeah, I want to avoid when the thing is too long. Okay, so let's see some exercise now. Oh, this is actually a statement, which is important, but so let's say this is actually a theorem, but I state this in the exercise. If E is measurable and the measure of E is less than infinity, then for all epsilon, there exist intervals I, fine, such that E, sorry, the measure of E. Okay, the symmetric, you like the symmetric difference of sets like this one? The union of I is less than epsilon. Okay, you have the two sides. So one will take the covering in order to get that this is less than epsilon half. And now this is a sum to infinity. And now being of finite measure, this sum should converge. So well, you have just to avoid if they superimpose each other, but you can do that, no? Just, and finally you make them disjoint. Okay, I leave to exercise. This is a nice exercise.
What is delta?
Delta is the symmetric difference. So A delta B is A minus B union B minus A. So it can be too large outside, but cannot be too large. So you cover almost all E, but you don't cover too much of the rest. This is a very nice exercise. Huh? I think we have a tutor for next week. Maybe I'll ask him to solve it. Let's do the significant point. Well, there are many exercises, but let's see one that is interesting. Okay. Because the problem is that I always think, well, since I know the theory, maybe I find it easy, but okay. Prove that if E measurable is equivalent to, for all epsilon, there exists C O closer open, and the measure of O minus C is less than epsilon. This is just how we apply the theorem. Okay? This is a little bit tricky. Let F, okay, let A be a measurable set. And assume that we have two cases. A, so E is contained in A, and the measure of A minus E is equal to 0. Or A is contained in E, and the measure of E minus A is equal to 0. Which one implies the measurabilities of A? Comes to the blackboard and then which one?
Second one.
Why? Yeah. The answer is true. But why? Well, maybe you can say both. So okay, let's see. Why the second? The second doesn't imply anything. wait a minute, which one? A minus A. The second, it's a set which is larger. Or did I copy correctly? Ah, no, sorry. No, the difference is 0. Oh, because here the difference is okay, it's this one. It's a measure of E. No, because then it's clearly true, because a set of measure 0, I'm saying the same thing. It is clearly, we both implies the measurability. No, because it's a set of measure 0 added to A or E, or subtracted to A, so still is measurable. This is the theorem. So which one of the two implies? I'm sorry. The second
M of A is equal to 0.
implies that is measurable or nothing. Measure. The definition of M star is that the M star of A is the infimum of M star of open set. So there is a G delta set whose M star is the same. So this is trivia from definition. Every set satisfies the second by the definition. So the second does not imply anything. Is automatically satisfied. You see why? M star of A is equal to the infimum of the sum, so let's say M of O open, and O contains E, A. Do you agree with this? This is the definition. I replace open sets, counter many intervals with an open set. And then if you take, let's say, counter many sets, so it is the G delta. And now the M of G is equal to the infimum, so it is M star of A. Ah, gosh, I'm sorry, I'm so I don't know why, this is the condition. You write and then you see what you wanted to write, but it's not what is written, no? Sorry.
I was surprised because you wrote 0, then it becomes M of A is equal to 0.
Yeah, I wrote twice the same condition. Okay, so, yeah, the second clearly, okay. You're right, now you understand. This one is empty. And this one is the true one. Because it says that E, so A is contained in this G, and contained in this A, and the measure of the difference is equal to 0. Yeah, one is contained in the other, they have the same value. And so it is measured. I'm really sorry. This is a very nice exercise and then I screw it up.
We don't need the measure to be finite.
No. Let me see, maybe yes. Yeah, we need a measure to be finite. Yeah. Because otherwise it can be infinite and not measured. Now let's the last one. Okay, show that if E is not measurable, then there exists open set and M star of E, let me write correctly. So E is contained in O, and M star of E plus M star of O minus E is greater than M star of O. Okay, now it's okay. Here you require that M star of E is less than plus infinity. And the thing is written here, no? Okay, I leave it as an exercise. But we can have different proofs here, even by using exactly the definition. Maybe it's even better. Okay, so question today. I think from the next week we start what is the Lebesgue measure, and well, basically we are finished. The construction of non-measurable sets and some strange functions. Okay, no questions? It's done.